Okay, let's unpack this. If you're building any kind of web application that actually, does something useful,
Hmm.
maybe it remembers who you are, your user ID, or it holds items in a shopping cart, keeps you logged in. It needs memory.
Right.
We call that state.
State is absolutely fundamental. You just can't build anything non-trivial without it. It's the historical context, the set of variables that define the system's condition from one interaction to the next.
Okay.
But here's the kicker, the paradox every single architect bumps up against. Your app needs that state to be smart, to be useful. But the instant you make the server remember that state, scaling just gets exponentially harder.
Right. That's the core tension we want to dig into today. We're looking at the two main architectural paths people take to solve this, stateful versus stateless.
Yeah, and really analyzing the specific trade-offs. What do you gain? What do you lose when you decide where that crucial memory, that state, actually lives? Our mission here isn't about declaring one the winner. It's about giving you, the listener, the framework to understand that strategic choice. Because where you manage the context of a user's journey, that decision pretty much dictates everything about how scalable and resilient your application will be.
Okay, so let's start with the problem itself. Why is it so hard? Before we get to the solutions, what exactly is this state we're trying to manage? I know there's temporary memory versus more permanent stuff.
That's a key distinction, yeah. When we talk about server state, often the immediate thought is ephemeral in-memory state. Stuff that's volatile, right? It disappears the second the server process stops or crashes.
Yeah.
But for a real application to actually work reliably, you need durable state, persistent state, things like user profiles, order histories, stuff that absolutely has to survive server restarts or failures.
Got it. And the simplest way, the most intuitive way, maybe, to handle this is what you call the stateful paradigm.
It is. It feels natural at first. In the stateful model, the server itself keeps track of all the client-specific session data from one request to the next. It actively holds onto the user's context right there in its own memory.
Okay.
Think of it like the old-school local bank teller, the one who actually knew you, remembered your name, maybe your last few transactions.
Right, they know your history on site.
Exactly.
Yeah.
You walk in, they pick up right where you left off. That continuous conversation, that shared context, it streamlines the whole interaction, makes it feel smoother.
That sounds really nice, actually, especially for the user experience. But you mentioned the simple model breaks down sometimes violently when you try to scale it up, like internet scale.
Oh, absolutely. It just can't cope efficiently when you throw thousands or tens of thousands of concurrent users at it.
What was the engineering breaking point there? What actually failed?
Well, you have to look back at something called the C10K problem. This was a big deal back in the late 90s, early 2000s. Servers trying to handle literally 10,000 simultaneous connections would just fall over. They'd collapse.
Wow. C10K. 10,000.
Yeah. And the root cause was often the simplest way people dealt with handling many connections at once, the thread per connection model.
So assigning one operating system thread to each incoming connection, why is that so bad? Sounds straightforward.
It sounds simple, but OS threads are actually quite heavyweight. They consume a decent chunk of memory and CPU resources just to exist. So if you have thousands of connections, you suddenly need thousands of these heavy threads.
Okay, I can see where this is going.
The server starts drowning in what's called context switching overhead. Imagine like a librarian trying to help thousands of people at once. They spend more time meticulously bookmarking exactly where they left off with person A before turning to person B, then bookmarking that before going to C.
Than actually finding any books.
Precisely. The server burns all its time and resources just saving and loading the state of all these different threads instead of doing the actual work like processing requests or serving data. You hit resource exhaustion. The system just chokes on its own bookkeeping.
Okay, so the basic stateful model hits a hard limit. And our sources mentioned this leads to something called the vicious cycle of stateful scaling. Sounds ominous.
It really is, because developers trying to salvage the stateful approach came up with workarounds. The most common one was sticky sessions, sometimes called session affinity.
Ah, yeah, where the load balancer tries to always send your request back to the same server instance that handled your first request.
Exactly. That way, the server that already has your session data in memory handles all your subsequent requests. It maintains that session continuity.
But now that specific server becomes a single point of failure, right?
Yeah.
I definitely remember the frustration of losing my entire shopping cart just because one server in a cluster had to be rebooted. That's the sticky session problem in action.
That's it precisely. You've traded one problem for another. You fixed continuity, but you broke fault tolerance. So to fix that problem, the single point of failure, you're now forced into doing complex state replication.
Meaning you have to copy that session data across multiple servers in the cluster.
Yes, synchronizing it constantly, which means network traffic, complex locking mechanisms to avoid data corruption, and you inevitably run into incredibly difficult data consistency problems. Is the state on server A the same as server B right now?
Oh, wow.
And all that complexity, all that overhead, it actually starts counteracting the original goal, which was to scale. You've added so much plumbing and potential for error that you might end up slower or less reliable than you started. That's the vicious cycle.
Okay, so keeping state directly on the application server creates a scaling nightmare. If that server-side memory is basically poison for scaling compute, is the answer just to, well, forget everything?
Fundamentally, yes. That's the core idea, the elegance, really, behind the stateless paradigm. In this model, the server stores 0 client-specific session information between requests. None.
So every single request has to stand completely on its own.
Exactly. Each request must be atomic, self-contained, independent. The server receives it, processes it based only on the information within that request, sends back a response, and then immediately, completely forgets the client ever existed.
That sounds like HTTP itself almost.
It is. That's a big reason why HTTP, being inherently stateless, allowed the web to scale to the size it is today. It doesn't burden the servers with remembering past interactions.
Okay, but wait. We established earlier that useful applications need state. You can't just throw away the user's shopping cart or log them out after every click.
Absolutely not.
So if the server isn't remembering, where does all that essential context, the user ID, the permissions, the cart contents, where does that memory actually go?
And that is the critical insight, maybe the third order insight here. State isn't eliminated. It can't be. It is relocated.
Relocated, okay.
The real architectural achievement of the stateless pattern is this powerful decoupling of compute from state storage. We make the application servers interchangeable, disposable compute units, and we move the state somewhere else.
So where does it move? What are the main strategies for relocation?
Broadly, there are 2 main places it goes. First, sometimes we push it to the client side.
Okay, like using browser cookies. That feels familiar. Usually a cookie just holds a session ID though, right? And the server still has to look up that ID in some internal data store, which sounds kind of stateful again.
That's the traditional way, yes.
Yeah.
And it does still require a server-side lookup. But the more modern approach, the one that really unlocks stateless scaling for certain things like authentication, is the JSON Web Token, or JWT.
JWTs. Right. I've heard of those. How do they avoid the server lookup?
Well, instead of just storing a meaningless ID, the JWT itself contains the actual state data, things like the user's identity, their permissions, maybe an expiration time. This data is encoded right into the token. And crucially, it's cryptographically signed by the server using a secret key. So when the client sends that JWT back with its next request,
the server doesn't need to look up anything in its own memory or database.
Exactly. It just needs to verify the signature using its secret key. If the signature is valid, the server knows the data inside the token hasn't been tampered with and can trust it.
Ah, that's clever. The request becomes truly self-contained, at least for things like identity and permissions. No need for a session store lookup.
Precisely. That verification is usually much faster than a database hit, and it makes that part of the application tier much more elastic and scalable. No central session bottleneck.
Okay, so client-side with JWTs is one option. What's the other main strategy for relocating state?
The second, and frankly far more common strategy for most application state, is server-side externalization.
Meaning
The application server itself stays stateless, but it relies on other specialized high-performance services running behind it to manage the state. These backing services are inherently stateful, but they are designed specifically for that job.
Okay, like what kind of services?
We heavily rely on things like distributed caches, think Redis or Memcached. These are optimized for very fast, typically in-memory storage of temporary data, like session information or frequently accessed results. It's volatile, usually, but super quick.
Right, for speed. And for the really important stuff, the permanent record.
That's where databases come in, of course. SQL databases, NoSQL databases. These are the ultimate source of truth, designed for durable, persistent storage of your core application data.
Okay, let me try and summarize this because it feels like a really key point. Calling an architecture stateless is kind of misleading shorthand, isn't it?
It really is.
What we really mean is a server architecture with a stateless application tier.
That is exactly the right way to frame it. The application logic itself, the part that handles requests, becomes incredibly scalable and resilient because we can spin instances up or down instantly without worrying about losing user sessions tied to a specific machine. But its overall success, its performance, its reliability, all of that is now completely dependent on the performance and robustness of those backing stateful services, the cache, the database.
So we haven't eliminated the hard problem of managing state. We've just delegated it. We pushed it down the stack to specialized systems designed for that purpose.
Precisely. We solve the scaling problem for the web server by essentially outsourcing the state management.
Okay, that makes sense. So now the practical question for someone building an application, which approach should you choose? When does stateful make sense, and when is stateless the way to go?
Right. This is where the architect has to weigh the trade-offs based on the specific needs of the application or even different parts of the application.
So if we map it out simply,
The core trade-off is this. Stateless primarily gives you massive scalability and fault tolerance. If one server instance handling requests goes down, who cares? The next request just goes to another healthy instance, picks up the state from the external store if needed, and carries on. The impact is minimal, usually limited to that single failed request.
okay, scalability, resilience, that's the big win for stateless.
Definitely. And stateful, on the other hand, the main benefit is potentially a more context-rich user experience, maybe slightly faster access if the needed data is right there in the server's memory already.
Right.
But it comes at that huge cost we talked about. Scaling complexity, fragility, the whole vicious cycle problem.
So when is that complexity and fragility actually worth paying for? Where do we still need stateful?
You accept the stateful model, usually within a specific component, when that session continuity is absolutely fundamentally non-negotiable. The classic examples are real-time interactive systems.
Like online games.
Exactly.
Yeah.
Online multiplayer games where player positions, actions, world state need to be synchronized near instantly across many active connections. Or think about collaborative editing tools like Google Docs, where multiple people are working on the same thing simultaneously. That requires intense, low-latency state management.
Okay, real-time interaction. What else?
The other big area is complex transactional workflows. Things like online banking, where a sequence of steps log in, check balance, transfer funds, confirm must happen within a secure, continuous, authenticated session.
Right, you can't have the server forgetting who you are halfway through a bank transfer.
Absolutely not.
Yeah.
Or maybe a really complex, multi-stage e-commerce checkout process. Maintaining that consistent state throughout the entire workflow is critical for transactional integrity. You need that guarantee of continuity.
Makes sense. So conversely, when is stateless the obvious choice? Which sounds like most of the time now.
It's definitely the modern default for anything where high availability and easy scaling are paramount. So that includes almost all high-traffic RESTful APIs. They fit the stateless request response model perfectly.
Okay.
It's also a core principle, almost a requirement for microservices architectures. You want each microservice to be independent, scalable, and replaceable. And statelessness is key to achieving that.
You don't want one service's failure bringing down others because of shared state.
Exactly. And things like content delivery networks, CDNs, serving static files, totally stateless. And perhaps the purest example of stateless design today is serverless computing, or functions as a service, FASO.
Right, like AWS Lambda or Azure Functions.
Absolutely. Think about AWS Lambda. A function spins up almost instantly, does its specific compute task, and then often scales right back down to zero when it's idle.
Because it doesn't need to remember anything between invocations.
Precisely. It's inherently stateless by design. If it needs any information from a previous run or needs to store results, it must rely on external services like calling an API, reading from or writing to a database like DynamoDB, or using object storage like S3.
Okay. But you hinted earlier that most complex real-world applications aren't purely one or the other. The reality is often hybrid.
Oh, absolutely. It's very rare for a large, complex application to be entirely stateful or entirely stateless across the board. The smart approach is almost always a hybrid model.
Can you give an example?
Let's go back to that e-commerce platform. Think about the user browsing products, searching, reading reviews. That part of the site is mostly read-heavy. It needs to handle potentially millions of users simultaneously, and the content is highly cacheable.
That screams stateless.
Totally. You make that part stateless, served maybe even by a CDN or highly elastic web servers talking to caches. Super scalable, super resilient.
But then
But then the user decides to actually buy something. The shopping cart, adding items, calculating tax and shipping, Processing the payment, managing the order, that's different.
Right. That's write heavy, needs consistency, transactional integrity.
Exactly. That part needs to be reliable and maintain state accurately. So that functionality might rely heavily on a robust, persistent, stateful data service, the database, maybe a dedicated order management system, even if the web servers handling the clicks leading to that transaction are themselves stateless.
So it's about applying the right paradigm, stateful or stateless, to the right component or job within the overall application.
That's the key. Strategic application based on the specific needs of each part.
Okay, bringing it all together then, what's the final takeaway for someone grappling with this?
The big picture is pretty clear. The industry has overwhelmingly shifted towards mastering the strategic allocation of state. We've largely standardized on building the stateless application tier, the part that handles the incoming requests and runs the business logic.
Because that makes the compute side incredibly elastic, resilient, easy to scale, up or down, easy to deploy.
Exactly. And we achieve that by pushing the hard problem, the state management itself, down into specialized, often highly managed stateful data services, databases, caches, message queues, workflow orchestrators. That's the fundamental blueprint for almost every modern cloud-native application you see today.
So we started this whole discussion by recognizing that applications need memory state to be useful. But holding that state on the application server itself makes scaling that compute power incredibly difficult. And we've realized through this conversation that the modern stateless approach didn't actually solve the state problem. It just cleverly moved the bottleneck.
That's a great way to put it. We made the application tier elastic and resilient.
But now the performance, the reliability, the scalability of our entire system hinges entirely on that now centralized stateful data tier that the stateless application layer relies on.
Yes, that becomes the new frontier of complexity.
Okay, so here's the final provocative thought for you, the listener, to maybe chew on. Now that you've hopefully got a good handle on designing a resilient, stateless application tier, what are the really big, thorny architectural challenges involved in scaling those critical stateful data services themselves?
Yeah, things like database sharding, partitioning strategies, ensuring data consistency across different geographic regions, handling distributed transactions reliably.
Because that's where the true scaling complexity often resides in modern systems, right? Scaling the things that the easy-to-scale stateless layer depends upon.
Absolutely. That's the next deep dive.